Welcome to cs1104 Computer Systems. This is the Unit 1 Lecture Part 1. During this lecture, we're going to cover some of the foundations of computer systems. We're going to start with chemical structures and bonding and how this aids or contributes to the flow of electricity. And we're going to end with gates and structures and how we can use these things to build computer systems. So we're going to cover a lot of material. So we want to just kind of jump right into it. Where we want to start with this is really focusing on the hardware of the computer. Most of the curriculum at the University of the People is focused on looking at software or developing of programs or using of programs. In this course, we're really going to focus on hardware. And we're going to learn a little bit about electricity and the properties of electricity that allow us to create switches and how those switches contribute to gates and how those gates can be put together to form computer systems. So let's kind of jump into this. The first thing we want to look at is talk a little bit about conductors. We know that some materials are conductors, or a material or a substance that allows electricity to pass through it. And other substances are not conductors. Glass, for example, is not a conductor. Copper, on the other hand, is a conductor. And one of the things we want to kind of understand is why. Why do some things conduct electricity, some things not conduct electricity? One of the things that we want to look at and kind of be conscious of is the idea of valences and electrons. So, for example, a typical atom is comprised of protons, neutrons, and electrons. The protons and neutrons form this part right in the center that we refer to as the nucleus. And the electrons fly around the nucleus in these concentric orbits. The outer orbit, the final one out for which there's an electron in, is called the valence. The valence shell or the valence orbit. And in the valence I have electrons. Now in some cases there's an unbalanced number of electrons, and when there's an unbalanced number of electrons, then the electrons can potentially be shared with other atoms. Now this is what we refer to as a bond. Now some substances, as you can see in this example of silicon over here, they have electrons that are always paired up. And when they're always paired up like this, that means that they can't really form bonds in the same way as atoms where the electrons are unbalanced, such as the copper atom here. So what does that mean? Well, if I look at a model of how electricity flows, what we see is that those electrons in the outer shell tend to interact with the electrons in the outer shell of other atoms that are sitting next to it. And they become partners. So the electrons can flow in between the multiple atoms. And that's essentially what's happening when we see electrical current. And in particular, when we look at metals, and metals, as we all know, tend to be very good conductors of electricity, the kind of bond that's being formed chemically is called a metallic bond. And essentially what happens in a metallic bond is that the electrons can actually bind to other atoms and flow somewhat freely between those atoms. And that's exactly what we're seeing in this model of electricity flowing through copper. We see that the electrons are moving freely between atoms in this metallic bond. So we know what happens with copper, which is a very good conductor, but what about silicon? So silicon in its pure form is not a conductor like metals. It can be coerced to move electrons, however. Now, what do we mean by coerced? Well, essentially, silicon is really not a conductor at all. But what we do to silicon makes it have some unique properties. So essentially what we do with silicon is that we dope it. Now when we talk about doping, essentially what we mean, and if you look at the model right here in the middle of the screen, we have kind of this lattice structure where all of these gray circles represent atoms of silicon. And in between some of these gray ones, I have a colored one, and that represents an atom of something else. And this is essentially what we mean by doping. It means that we introduce an impurity into the structure of the silicon atoms. Now, there are two kinds of doped silicon. There's one we call an N-type, and an N-type silicon is one that is doped with the materials arsenic, phosphorus, or antimony. So when I dope it with one of those three, then it becomes an N-type silicon. And essentially it has it becomes a material that has extra electrons to lose. So it can hand electrons off to another substance. in a bond. On the other hand, we have what we call p-type silicon. P-type silicon is silicon that's doped, or in other words, we have some of these impurity atoms put inside of in the silicon, but it's something that's doped with boron, gallium, or aluminum. So p-type silicon is a material that has the ability to gain electrons. Now, what do we do with that? Well, in computers, the primary thing that we have, and the thing that's very important, is something called a transistor. And a transistor is essentially an electrical switch. A transistor gives us the ability to turn current on and turn current off. And it's this ability to turn electricity on or current on and turn it off that gives us the properties necessary to actually create computer circuits. So the way that we make a transistor is that we kind of sandwich together different layers of silicon. So for example, I could layer some p-type silicon in between two layers of n-type silicon, as we see in this particular example. Now, the n-type has the ability to, as you recall, lose electrons, and the p-type has the ability to gain electrons. And essentially what happens is that the electrons will kind of come into this side of the transistor, and they wind up getting stopped at the base because the base has a different characteristic. So they don't quite make it all the way through. And generally what we want to do is we want to be able to move electrons from the emitter all the way over to the collector. Well, we can't do that. What is unique about the properties of silicon is that if I apply a current to this thing called the base, essentially it will change the characteristics of this silicon such that the current will flow. But it will only do so as long as that circuit remains enabled, as we can kind of see in the example down here. Essentially what this does is by layering a p-type between two n-types, or conversely, I could put an n-type between two p-types of silicon, it gives me the ability to have a controllable switch for electricity. Now, how do I make these, and how does that translate into computer circuits? Well, imagine, if you would, that we need to have this structure where I have, I have my silicon, and I have three different layers. I might have an n-type, a p-type, and another n-type. And essentially I want to have this kind of a structure because this is what allows me to develop the switching properties of the semiconductor. Well, imagine, if you would, I were to set this on its side such that I have some base material, which is in fact n-type silicon. I have a middle section that I layer on top that happens to be p-type silicon. And then I have finally on the top of that another n-type. Essentially, this is exactly how we make integrated circuits. I start with a base wafer, if you would, of silicon. And on top of that, I layer some of this doped silicon, some of this n-type silicon. And then what I do is I etch away a pattern of everything that I don't really want. And essentially what I'm trying to do is I'm trying to create the characteristics of the layers of this circuit. Now, on top of that layer, once I've etched it, I will squirt on and spread over like peanut butter some of this p-type silicon, etch it away, and then finally I'll put another layer of the n-type on top and then etch away to just the characteristics. And you can kind of see these pictures here that show these various characteristics of n, p, and n-type silicon layered on top of each other, and done so in a pattern that I etch away such that I can have a number of different transistor structures. In fact, if you go out on the internet and you kind of search for something that would show you an integrated circuit transistor, you'll see exactly what they do in terms of how these patterns look when they get etched. And essentially that's how we make an integrated circuit. We literally build the transistors by a pattern layered one layer on top of each other at a time. So once I've done that, I wind up having this structure. We call it a transistor. And by the way, there are two different types of transistors. We've already really talked about this. One of them is I have a n-type silicon layered between two different p-types, and we refer to that as a PNP transistor. And the other one is obviously just the opposite, which is I have in the middle a p-type silicon that is is sandwiched in between two n-types. Now, when I look at the circuit diagram of a transistor, they're going to kind of look like something like this. And they will always have this long bar, and this long bar represents the base. The base is this material that's in the middle. It's either going to be n-type or p-type. And really what the difference is how I electrically form the circuit between this. But essentially, when I apply a circuit that energizes the base in both of these cases, essentially it turns the switch on and it allows current to flow from the emitter to the collector. So you can kind of think of this as it's emitting the electrons here, it's collecting them over here, but essentially it's allowing current to flow through. So I turn the light switch on, and I do that by energizing the base over here. And this just gives us a little picture of how that circuit works. So I kind of apply electricity to the base, and then what it does is it allows the current in this circuit to flow through. When I turn this off, the circuit turns off, and the current here can no longer flow. Now, how do I use that? Well, I don't know if you've looked at these or have seen these symbols before, but these are a series of symbols that we refer to as logic gates, and they have a very specific meaning. In fact, every one of these symbols on the left-hand side has what we call a truth table on the right. And when you look at this truth table, it basically is telling us what the inputs are and what the outputs are. Think of inputs as the presence of electricity or the lack of electricity. So whenever I have a 1, that means there's an electrical voltage present. Whenever I have a 0, that means there's no electrical voltage present. And essentially, I have an input side and an output side. So if I look over here on the AND gate, it says an input side where I have an A input. So perhaps this is the A over here. And this is my B down here. So A and B input, this over here is going to be the output, and then we can see the truth table. And basically what this says in the AND gate is that when I have a voltage on A and a voltage on B, I have a voltage coming out on the output. It also basically says if I have a voltage on A but not one on B, there's no voltage coming out. If I have a voltage on no voltage on A, but I do have a voltage on B, nothing comes out. And when I have no voltage on either A or B, nothing is coming out. Basically, this forms a truth table, an on-off or binary type of a situation. And I have different gates that have different characteristics. Now, why this whole discussion of transistors was important is because it gives us an understanding of how these gates are actually constructed. Now, we're going to go in the next unit, we're going to find out exactly why these gates are so important. But what we really want to look at here is just exactly how these gates are formed. And I have the circuit diagrams for a number of different gates. So here I have the NAND gate, here we have the AND gate, the NOT gate, and the OR gate. And we could come up with the circuits for all of the different gates that we saw on the preceding page, but I just wanted to give you a couple examples. In this particular one, we can see that we have two transistors. We have the transistor for A and the transistor for B. You'll notice that we're measuring the output right up here. So our power comes in right here, right? This is where the electricity is flowing in. And under normal conditions, I should have an electrical current coming after the outside, right? And the reason why I do is because this switch is not on. In fact, the way that I have to turn the switch on and allow the electricity to flow all the way down is that I would need to turn this transistor on, and I have to turn this transistor on. And one of the reasons we call this a NAND gate means not and, not in this particular case meaning that it's turned on by default. So normally the output will be 1 unless I turn A on and B on. When I turn A and B on, current's going to flow down. It's no longer going to have the voltage here, and it has the characteristics of a NAND gate because of that. Now, the AND is kind of exactly the same circuit, but backwards. In the AND gate, you'll notice here that this switch is turned off, right? Unless I apply something to A and B, the switch will actually be turned off. So normally, the output is 0. If I turn A on, so this transistor turns on, so current is able to flow to this point, and then turn B on, current can flow all the way through. And when it flows all the way through, then I have this opportunity to measure a voltage here. So we get a sense for how the NAND and the AND works. NOT gate, very simple, single transistor, and same kind of a principle here. I have a normal value of 1. right here. And if the gate turns on by applying the voltage here, essentially the current's going to flow all the way through, and this thing's going to go to 0. And over here, I'm showing an OR gate. The OR basically means that if either of the switches turn on, then the output's going to turn on. And so essentially in this case, it's going to be output is going to be 0 unless either A is turned on. So if A turns on, we can see that the current flows through the circuit. Or if B turns on, in which case also the current would flow through the circuit, and then this would become a 1. So it gives us a little bit of view of how the gates work, how they relate to transistors, the fact that transistors are built on top of semiconductors, and it's this unique property of semiconductors that allows us to kind of coerce some electrons to flow through the material, even though it's not normally a conductor, by doping it, or doping meaning that we introduce some sort of an impurity. This is the foundation upon which all computer technology